In this demo, we'll connect the 12-volt ungeared stepper motor to the L298N motor controller. Let's assemble the circuit first. Beware that in the schematic here, the power supply for the motor looks like a 9-volt battery, but in fact should be a DC power supply that can provide 12 volts. The motor is a unipolar one with 6 wires, 2 of which are the split ones and I'm not using. Your motor may actually have 5 wires, which means that the split one are common for the 2 phases, and you should leave that one unplugged as well. Your motor, if you're lucky enough, may come with a diagram showing you which wires are for the coils. If you have the same as mine, 12 volts, 48 step, 7.5 degrees, then coil 1 is orange and purple, and coil 2 are yellow and blue. Another thing you can do is to use a multimeter in order to figure out which wires make up the ends or the end bits of the 2 coils. Resistance between coil and wires is around 38 ohms, while resistance between coil and common or split wires is half of that, around 19 ohms. So in this first demo I'll show you a couple of things. Of course I'm going to show you how to connect your motor. This is the ungeared version of the unipolar motor to the driver breakout, which is the L298 based one we used in the DC motor demo. First though, I'd like to show you how to use the multimeter to figure out which one of these wires connect to the ends of the coils and which ones are connected to the midpoints for the 2 coils. So the version that I have here has got in total 5 wires coming out of the motor. So one of them is the common midpoint wire. So I've set my multimeter to measure resistance. So it's at 200 ohm maximum resistance. So I'll pick those 2 wires and so I've numbered them. That's number 1 and number 3. So resistance between these 2 is 38 ohms. So these 2 make up the ends of the first of the 2 coils. These 2. So another 37.5 ohms here. So these 2 make the ends of the second coil. Now this one, already obviously detected this earlier, but this one, if I measure resistance between this number 5 and any of the others, I get 19.1, so approximately half the full resistance between the cables connecting the 2 ends of each coil. So that tells me that this is the midpoint cable. So I get the same half resistance regardless of what other end, or regardless of the cable of the other end of the measurement. So 19. Yep, 19. So in my demo, I'm not going to use the common midpoint cable. So I'm just going to get it out of there, and I'm going to continue with the connections. So for the power supply of the breakout, I'm using this patched cable version from a unit and power supply. It provides me with 12 volts out. So I want to have a common ground. So I'm going to take a black jumper wire and tie it neatly against the ground wire coming out of the power supply, and I'll stick that in here. Oops, I had contact here for a second. So stick that there. I'm going to connect the black jumper wire into one of the ground pins on the Arduino. So then the red is the plus 12 positive voltage. Stick that in here. Okay. Now, I've already labeled these to make it easy for me to plug and unplug the motor into the breakout. You may need to experiment these. If you plug yours in at some random order and you see that your motor isn't turning smoothly, then you have probably mixed the coils. So you can just play around with the connections until the movement that your motor is producing is nice and smooth. Okay, done with this. Now, to make it easier to connect the inputs, I found this nice 4 jumper wires connected together. So I've got the yellow, which is input 1, and input 1 I've already set to be digital pin 8 on the Arduino. That goes to 9, 10, 11, so I'm just going to plug that in here, and we are good to go. Also, the common ground goes here. Alright, so I'm going to plug this in to my computer. I've got some sketch happening here from something I tried earlier. This is not the sketch that I want to show you though. So I'm just going to upload it just to get this motor to behave a bit nicely, a bit better. Alright, and that's what it does. So 1 full revolution on one side, 1 full revolution to the other side. If I try to hold it and restrict its movement, yep, it's quite possible. So the torque in these small motors is not that strong. So I can just hold the rotor still. Okay, something like that. Reduce the noise. So let's have a look at the sketch now. So we start by including the default stepper library that comes with the ID, stepper.h. In the next line we define a constant, it's an integer, in this case it's 48, and all that is the number of steps that the motor is required in order to complete a full revolution. So 48 step motor means that this shaft needs to revolve or step ahead 48 times in order to complete 1 full revolution. So different motors will have a different number of steps per revolution, but that depends a lot on the number of phases that the motor has. So it seems that in most 2-phase motors, the steps per revolution is always going to be 48. In the next, in demo number 3, I'm going to show you a geared motor where this number actually differs. We're going to need to do a lot more steps in order to complete a full revolution. Now in the next line here, I'm defining an object called myStepper, which is of type stepper, and I pass a number of revolutions required, so a number of steps required for a full revolution, and the digital pins to which the motor is connected to. So in my case it's 8, 9, 10, 11. So you had a couple of stepper motors connected, then you'd need to use 2 different sets of digital pins. In the setup function, I first set the speed of the motor. So set speed and then passing in an integer tells the controller how quickly to move from one step to the next. So I played around with my motor and detected that 300 is the maximum that it can take. I'll show you what happens if I increase that, say, to 600 in a minute. That's it. Now in the loop function, I use the step function and pass an integer, which is an integer that represents how many steps I'd like my motor to move either ahead, or if that is a negative integer, backwards, so counterclockwise. In this case, I just pass 48 steps. I want a full revolution, wait for half a second, then pass negative 48 steps and wait for another half a second. Now before I go, let's change that perhaps to 600 and see what happens if I try to get the motor to spin much faster than it's capable of. So you can see that it's skipping a lot of steps here. It's not even doing half a revolution, so it's almost random, but it's definitely skipping a lot of steps. If I make that 900, yeah, it's not even going to move now. So the pulses coming out of the controller got into the motor so fast that the motor just has no time to adjust the shaft, so that's basically just skipping the steps. So play around with this to find the optimal maximum speed so that your motor is not missing any steps.